Welcome to second lecture of course on data-enabled tribological engineering from experiments to predictive models. The topic of this lecture is tribological interfaces. In my view, tribological interfaces play a very important role. Just to illustrate that, I'm going to show you a couple of the pictures. You can see here the gear picture or gear pair picture, and we can say this is a tribo interface under dry case. There's no lubrication, and under moisture case it has got corroded. Now we have another picture where we are showing tribo interface under lubricated case, because this is yellow color is a lubricant and we are able to see the lubricant at the interface. To simulate any of this gear, we often use two cylinders in a some sort of interface. So that's why we say it's a simulating tribo interface. With the radius R1 is maybe the pitch circle radius of the gear 1 or pinion, and R2 is the pitch circle radius of gear 2. I have shown another one, a sketch of the thrust ball bearing. Now there are too many interfaces in this case. Particularly you are able to see there is a one race this side, one race this side, and there are balls. So there is an interface between this race and ball, this race and ball, and there are number of balls. So there will be number of interfaces. And quite possible there is a full complemented bearings, then the number of balls will be too many, and there will be interface between this ball and this ball also. However, if these are lesser number of balls and we are using cage to keep their space equal, then we need to use a interface for the cage and ball. So there are too many interfaces, particularly when we are talking about thrust ball bearing. Just to simulate those, we often use, if this is fair and this is fair interface, something like a ball versus ball. When we are using the ball and concave interface, then we say there is a cage and ball, and we use a flat, that's a race and ball. So these are the kind of the simulation we use to simulate the tribo interface. Reason being, tribological interface plays major role in tribology. Unless we understand this interface, simulate this interface properly, we cannot really predict what's going to happen in tribology. So that's why we say simulating sliding and thermal contact, both we are using the word. Reason being, if there is a sliding and there is a friction, and friction is very high, then there is a possibility of heat generation, and if there is a heat generation, then there will be instantaneous high temperature at the contact. So that's why we say we need to simulate thermal contact also in this situation. Reason being, all this will affect what will be instantaneous stress. An interesting thing, in mechanical engineering, when we talk about the stress, we talk in MPa, but when we talk about stress in tribology, we talk in a gigapascal, is almost 1000 times higher, or maybe say 100 to 1000 times. Then friction and wear, everything will depend how the tribo interface is behaving. If a tribo interface behaves very nicely, then friction will also be lesser, wear will be almost negligible, temperature will not rise to much level. So this will be the helpful. So that's why we say tribo interface plays major role, and that's why we have kept a one complete lecture on tribo interfaces. Now let's start again with the tribo interface. We say that we are using the word tribology here. Reason being, it is a friction, lubrication and wear, and often we use the word friction and wear for tribology, but we need to also include the lubrication. How do we include lubrication? We'll be covering in this lecture and next lecture. So what we are trying to convey here in this case, the friction and wear, which are characteristics to define a tribology, they are not just material and specific. That's why you say that friction and wear are characteristics of a system rather than a specific material. Reason being, many times people publish the data, something like that, there is a virgin metal sliding on themselves, like aluminum versus aluminum, coefficient of friction will be 1.5. Copper versus copper, then coefficient of friction will be 1.5. Gold versus gold, coefficient of friction will be 2.5. So this is somewhat I feel that something is missing. Reason being, the coefficient of friction will depend on the roughness, it will depend on environment, it will depend on load, it will depend on speed, temperature and lubrication. So there are so many other parameters other than materials. So that's why we are writing here, it is not property of a specific material, it's a property of the system. And when we try to simulate the system, we need to account more number of factors. So that's why it is becoming important for us. And we say the surface interaction determines the friction and wear characteristics. Again, I don't want to say is the only surface interaction. Naturally, there will be environment, load, speed will matter a lot. So that's why we say that it is also surface interaction. It plays important role. Of course, when we do the machine learning and we use a PCA to figure out what will be the contribution of each parameter. That means there's a one parameter, second, third, fourth, fifth, sixth. Out of six parameter, which parameter will affect friction and wear majorly? That will be decided maybe it's the second part of the course after lecture 18. And this will be important reason being quite possible some factor will affect more on the friction, some factor will affect more wear rate. So that's why we need to understand. Now what will we are trying to understand in this case a surface interaction, and we have already learned something in lecture 1 that every surface is made of few layers. So that's why we say that surface doesn't mean that the top layer but a few layers. It can be contamination, adsorption layer, oxide layer, work hardening layer, which is happening on the metal surface. So we count 5, 6 layer, top layer as a surface. Why we are counting these top 6 layers? Reason being that every surface is a rough surface. So if I look at the micro scale level or nano scale level, so this is a micro scale level, I will find a surface very irregular. You can see here, and then it maybe if you look at the macro scale, quite possible the surface looks like a perfectly flat. But when you go to the micro to nano level, you will find there are many peaks and valleys. Naturally, when there are many peaks and valleys, and as a load is applied on that, in addition, friction force is applied in tangential direction. What will happen under mechanical load or W? This asperities will try to dig into the asperities of other surface. That means asperities of surface 1 will try to dig in surface 2. While coming to the friction force or tangential force, that asperities will try to remove this asperity, displace this asperity one way another way. If this surface is a harder and this surface is a softer, quite possible this asperities will be breaking. So this is an important aspect to consider whenever we deal with a tribology. We look at the interface, look at the surface roughness, and surface roughness becomes very important to tell us what kind of friction, what kind of wear rate will occur. That means if there are too many asperities, both friction will be higher, wear will be higher. If the perfectly smooth surface, even angstrom level surface are smooth, quite possible wear initially will be lesser, but friction may be higher. Reason being, extra smooth surface, they will have a high molecular attraction. So naturally friction will be on the higher side. So these are the important aspects. That's why we have kept this complete lecture on the tribo interfaces. Now we talk about something like a surface roughness, and we also have studied earlier that whenever these rough surfaces they come in a contact, they will make a contact at the only few points. It's not a whole surface area will be in a contact as such. So that's why we say here surface roughness refer to how far surface deviates from a perfection. I'm using the word perfection means a straight line in the situation or in a straight plane. Then we say surface roughness comprise of flaws. We are using the word flaws, maybe peaks and valleys are there. And then particularly we want to emphasize on the low wavelength high frequency signals. Reason being, uh, complete surface is made of the three things we will be discussing in this lecture, and lowest one is a surface roughness in that. That's why we are using the word low wavelength. Then we will be coming to the other aspects, and we are more interested on in low wavelength. It may be scratches also, and maybe pits, maybe grooves, and then we need to really consider all those things. Another thing what we are saying, the tribo interaction between solid occurs in a fragment manner. It's not a continuous manner. That means the continuum theory which we generally use for hydrodynamic lubrication, that may not be applicable for this purpose. Reason being, the contacts are happening on a fragment manner. It is not happening in continuous manner. It's are point wise. So that's why there are a number of points considered in this case. Another thing is that these patches which come into contact, they may vary in size, they remain unequal, uneven shapes also. And we also mentioned in last time, last lecture, that actual area of contact is much lesser than nominal area. So if I say this is a nominal area or apparent area AP, and this is a real area, what we generally say AR is a far lesser than AP. When it happens for the same force, what will happen in the situation? Stress level will increase significantly. So if I'm assuming the AR is just 15% of AP, naturally the stress level is increasing 6 times. That's what we say in mechanical engineering. We talk about a megapascal, but when we talk about tribology, it increases by number. That's maybe 6 times, 7 times, 8 times also. That's much higher stress. And many times in mechanical design, we say that elastic deformation or elastic strength or yield strength, that doesn't work for the tribology. We believe that in tribology, most of the asperities which are coming in a contact subjected to high load will be subjected to plastic deformation. And that's the reason we say that when two surfaces come in a contact, initially there may be some surface roughness, but it will alter, it will change over the time. And that's why we again say tribology is a time dependent. Whatever the situation today, it may not be for the next hours, next 10 hours. So this is what we need to model all those level, and that's why we are using machine learning algorithms for this course. So this is what I wanted to show. If the surface roughnesses are not there, then this will be the perfect kind of the plane where the two surfaces will come in a contact, and then here the apparent area, it will be very high, apparent area will be high, and then real area will be equivalent to apparent area. Stress level will come down. So some of the extra smooth surface will be preferred from that point of view. But in reality, when we go to the nano level, surfaces are rough. We find a lesser number of surface contact happens, or apparent area is higher compared to real area of contact. Now we have a discuss about this, and this again I'm bringing the figure from lecture 1, where we studied something like about a gear pair, and we say that when they come in a contact, there are three chances. One is the asperities will break, elastic deformation will occur, and plastic deformation. Quite possible 5% possibilities asperities will break, 65% possibility is that elastic deformation of the asperities will occur, and 30% asperities will undergo the plastic deformation. They will change the shape, and that's why reason the with the time, maybe say initially itself. So we have a demonstrated initial position of the pinion and running in position of after running in situation, what will be the shift in the profile. So initially it was a dotted profile, now it's a and the form line profile. So profile also will change, and that's why we say that plastic elastic deformation will take place on a surface which are in a contact. Now how much plastic, how much elastic, mostly it will depend on the hardness. if hardness is on a higher side, naturally more deformation will be because of the elastic deformation. Lesser is deformation will be plastic deformation. However, the hardness is a lesser, or in the situation plastic deformation will be dominating compared to elastic deformation. And whatever we say running in behavior, it will occur in both the surfaces. In harder surface, softer surface, in both the cases the running in behavior will occur, and we need to account that into our analysis, our mathematical model and the computational model, and that is a very difficult, and that's why we really require a sophisticated method to model this kind of behavior. Now, again, as I mentioned, tribology depends on the time. Here I'm trying to show the friction depends on the time, wear depends on the time also. So this will change with the time. What we are saying, the sliding in a dry contact, particularly we are not yet started a lubricated contact in this situation, will go through running in period. What is the meaning of that? Initially the surfaces will be in a contact at the particularly this, or there are, suppose there are asperities, they will come into contact, and one of the surface will be harder compared to other surface. So what the harder surface will try to blow the softer surface by asperities itself, and then whatever the results we predict, friction results which we predict in the situation will be friction primarily will be result of flowing. That means whatever the energy loss in a flowing, that will cause a that will be helping us to figure out what is the friction. In those situations, particularly adhesion between the surfaces will be relatively low because real area of contact is much smaller, and the adhesion will occur only on real area of contact. More or less, it will be lesser compared to the friction caused by the flowing effects, and that has been shown here when the two surfaces come into contact. Now, if they come perfectly in match, then quite possible this interface remains stronger compared to the weaker material, and a whole material will get transferred, and this is what we call adhesion, friction caused by adhesion in the situation, or this adhesion is strength itself, and whatever the strength, the force which will be created, it will be like a cold weld junction, and strength of cold weld is a more compared to the strength of material 2. In this case I'm using the word is a material 1 and this is material 2, and cold weld strength itself will be more compared to the material 2. That's why the whole piece is getting transferred, is shifting to the material 1. That's what we call as adhesive wear. We will be discussing in a lecture 4 about this. However, as I mentioned, the flowing effect that has been demonstrated over here, the plowing effect is something like harder asperities trying to dig out, trying to plow the softer surface. So in this situation, this is the softer surface, this is a harder asperity, and this has been shown that friction will be mainly because of the this plowing effect. However, we talk about the running in period also, that happens, and that's shown on here, that particularly when surface 1 and surface 2 come in a contact, and quite possible surface 1 has a slightly brittle in a nature when they are sliding with surface 1 is sliding against surface 2. One possibility is that initially it is a harder as well as a brittle, harder and brittle both, while this surface is a soft surface 2 material, material 2 or maybe surface 2. What will happen, asperities will try to dig some sort of grooves in material 2 or surface 2, but after some time maybe these asperities they act like a cantilever, and then they get shaved also, they get removed from the surface 1, and quite possible they will try to fill the whatever the grooves they made in the first earlier 1000 cycle or 10,000 cycles. So this asperities will also get settled there, and that's why we say it's a shaving of the particularly asperities and filling the gap of the opposite surfaces. So this is a running in period. What measured the meaning here, initially surface 1 was a rougher surface, even surface 2 may be rougher also. So after removal of the asperities from a surface 1 and bridging of the gaps using by those debris of the surface 2, both the surfaces will turn out to be having a lesser surface roughness compared to initial surface roughness, and that will act in better manner, and that's why we say that this need to be modeled properly. Now coming to the earlier table which demonstrated or showed an earlier slide, and then we show the coefficient of friction. Basically this coefficient of friction, we understand the value comes when the materials are tested in a vacuum, or when there is a no air, there is no atmosphere, and then in the situation there is no oxide layer also. That means if there is a no contamination layer, there is no adsorbed layer, there is no oxide layer on a surface, then getting this kind of wear coefficient is possible. However, if these contamination layers are there on a surface and then they are not getting removed, and there is a sufficient time, even the one layer gets removed, second layer is getting formed on the surface, then we will not get this kind of coefficient of friction, and the coefficient of friction will be basically lesser than this kind of values. Like in the platinum, and the platinum instead of 3 it may turn out to be 0.8, 0.7, something like that. However, depends on the what kind of contaminations are available in the environment. If it is a vacuum, we may get this kind of surfaces. So naturally it depends on what kind of circumstances are there, what kind of environments is there, so that it will really decide what will be the behavior of the materials in a contact. That means tribo interface plays a major role in overall tribology. Now continue with this. As I say, that friction and wear will be depending on the time, and we already demonstrated this figure earlier slide, this figure earlier. Now this is a new figure, and we say the coefficient of friction in this case initially will be higher, reason being the asperities are on the higher side, and then shaving of asperity is not happening, and then the flowing effect is dominating factor. And quite possible after that this material is coming from surface 1, surface 1, surface 1, and then they are getting settled into the grooves of some material 2. So these grooves are acting as a pocket or like a dustbin for the material 1. Now these debris are not playing much role, and the surfaces are already kind of the smooth surfaces, not perfectly but better than the earlier one. So in this situation coefficient of friction will drop down. So coefficient of friction initially is something like that, it's coming down this, and it will remain for the some time. Now there is, depending on the kind of the circumstances, it gets some sort of expertise in they which are initially getting filled in and the grooves may get tilted or maybe coming out. Quite possible that the friction again will increase. If these asperities start abrading the opponent material or getting deposited on opponent material, then quite possible we may get this curve. That means this has come down, and now here from here again we may get started getting rough surface, or maybe still this is only 10 to 5 cycles, and then still it is in good shape. Quite possible we may get after this, or maybe get after this. So 10 we may get a versus effect after 10 is to 7 cycle, 10 is to 8 cycle, 10 is to 9 cycle, something like that. But friction behavior will change with the time, and same thing happens with the wear also. Now if the friction is increasing, quite possible the wear also changes. I'm not using the word exactly changes, but may change in the situation, and then they follow the similar kind of curve. And if this is a kind of curve which we are known for the wear relation, we call the bathtub curve. We'll be describing in next lecture on the bathtub curve on this. So what has been written over here is a rupture or breakage of asperities provides some sort of polished surface to us, and because of that it will reduce the flowing coefficients but increase the coefficient of addition. Now one effect is coming down, other coefficient is increasing. So if I say the flowing coefficient is there and there is a addition coefficient, one is reducing, other is increasing, doesn't mean the first is decreasing by 50%, others may be increasing by 1%, 2%. So we need to investigate when we really start working on the friction estimation. So this is what we are trying to provide a pointer, that we need to really think about these lines. Another one is a polishing wear process can remove the contaminants. As when we do a polishing, quite possible the top layers are getting removed. There's a possibility also, and there's not a sufficient time that other layers are getting deposited on this surface. In the situation, what will happen, it will reveal the bare surface, a virgin material, which is much more reactive, and then quite possible immediately the addition happens, and then coefficient of friction increases. So this is also important when the surfaces are under contact and undergoing through the deformation or dislocation, and then if the it is bare surface or virgin surface is getting revealed, then possibility is that coefficient of friction again increases in the situation. Now, in this situation again there is a possibility, as I say, that where debris which are coming out from a surface 1 in this situation, they don't get a grooves properly and they get entrapped in there, then it will be the problem, and that's why we say the wear debris trapped between the two sliding surfaces may cause a higher wear rate. So we have all the chances. We are not saying it is going to definitely happen. Friction may increase, friction may decrease, wear may increase, wear may decrease, but we need to know what are the factors. So this is what we use a word, the feature identification. What are the features which are really important for us, and this also will be covered in second part of this course, maybe uh, after lecture 18, that what are the features which we need to count, particularly when we are estimating tribology, when we are talking about friction, we are talking of the wear rate. And then here particularly when what we have shown as this as the blue color line in this case, let's say that possibility is that a steady state friction condition may be established, and then particularly for after the running in wear worn out surfaces. Worn out doesn't mean in the situation a complete wearing out surfaces. Initially that means whatever the asperities have been removed, it has been either getting removed completely from the from interface, or it is a finding some slot to get settled there. That's what we say, that it will, in this situation maybe the condition will be established and will be normal for us. Now another one thing is characterization of the surfaces. We really require how to really characterize this surface roughness. What are the really important parameters, very important factor, because that will be really required for understanding concept of friction and wear, which is our next lecture. In lecture 3 we will be focusing on friction and wear, but in this lecture we are trying to focus on tribo interface. And because in tribo interface there are two surfaces, how do we characterize the surface, how do we quantify the surface, that's important, and we'll be considering in the present lecture those aspects. Now in this there is a slide which I have been picked up from a literature as such, and what we are trying to show that surface roughness, we have been talking something about surface roughness, it has some sort of amplitude or magnitude, but there is also possibility of the different kind of surfaces, surface roughnesses. It's not a surface roughness means only one, it can be different. Like in this case particularly, that sliding direction has been shown, maybe sliding direction is parallel to this type 1, and there are micro grooves you are able to see. In this case there is a micro groove here, micro groove here, micro groove in this situation, and this is basically lubricated cases. So what happens in the case of the lubrication, quite possible these grooves provide easy passage to drain the lubricant. That means lubricants are not fulfilling the meaningful purpose, and before that they are getting drained out. So this is sliding direction, and then groove direction, they are matching. While in type 4 we have a perpendicular, maybe it's not visible completely. So if the sliding direction again is this, there is a possibility of the groove perpendicular direction. Now in this situation I can really do a good design. Even for this case we can really do a good surface design, and we can block these slots over here. Of course we really require to design, and those things will be discussed in lecture 13, surface modification techniques, which are really important for typological applications. While in type 2 and type 3 are the more or less same, they are kind of a pattern has been made we don't really go through this groove arrangement or this groove arrangement. And this has been published, that there are this type 1, type 2 and 3 are more or less same. Type 4, you can see here the type 4 is really showing a low coefficient of friction. So it's not a magnitude, it's a type of the surface roughness, and that is relative to the sliding direction. While type 1 is gives a maximum coefficient of friction, while type 2 and 3 both are giving more similar kind of a coefficient of friction. Now it's not only this, we are also seeing that magnitude of the surface roughness. As the coefficient, the surface roughness is going on hard side, we are finding some sort of random behavior in this case. That means it is a changing with the time. Now depends on the load situation. It may increase coefficient of friction, may decrease coefficient of friction. So we may expect a quite a random behavior of coefficient of friction. It may have some sort of a range. Quite possible coefficient of friction doesn't remain equal to, maybe say, COF, coefficient of friction. Somebody says a zero point 0.3, quite possible it may not be the zero point 0.3. There is a possibility 0.3 plus minus 0.1. That means coefficient of friction will vary from a zero point 0.4 to 0.2, or maybe say 0.2 to 0.4 in the situation. So it is very important, and it becomes a statistical. And as we know that surface roughness itself is a statistical. We have seen a continuous change in peaks and valleys. So those things are very important to understand. There's a need to really quantify this kind of behavior. Now one more figure is available in literature, which I'm trying to illustrate over here. Here what is the topic, the title I have given: surface roughness, interface and lubrication regime. We have picked up this relation from lecture 1, which where we say the specific film thickness, which is a ratio of film thickness, what is the separation. Now this is the film thickness, or H minimum in this value can be located. This is H minimum in this situation. So when H minimum is bigger or much higher compared to surface roughness, we are able to really look at see the hydrodynamic region as such. So if surface roughness is a lesser, then quite possible a specific film thickness will be on higher side, and a specific film thickness is on the higher side, we will be moving from this side to this side. This is what we say. Specific film thickness in this case will be 0 kind of thing. H minimum is 0. Now whatever the surface roughness, specific film thickness will remain 0 irrespective of the surface roughness. So it doesn't depend on that. Now here it is coming something like a mixed lubrication or boundary lubrication. We can really different. It is difficult to differentiate between mixed lubrication and boundary lubrication. People have used the word boundary lubrication, mixed lubrication, but I believe the mixed lubrication itself is the right word. Reason being, the few asperities are coming into contact, few asperities are not coming into contact, and there is a separation. So it can be treated as a mixed lubrication instead of definitely saying that it's a boundary lubrication, because different books really treat this specific film thickness. Some people say that there is a lesser than one, it is a boundary lubrication. While it doesn't make much sense to me, I'll treat this as a, if it is a specific film thickness is a greater than 0, then I'll say it's a mixed lubrication. Of course, if there is a complete separation, something like this, then the hydrodynamic lubrication will come. So I believe that it can be generally greater than 2 or 3, then hydrodynamic lubrication may come. Of course, it depends on situation, depends on the whatever the condition. So we can go ahead with this relation initially for understanding purpose, but for detailing purpose this relation may not be required, because we need to account all, whatever the interaction happens we need to account. If it is a hydrodynamic, we need to account. If it is a elastodynamic, we need to account. If it is really asperities, we need to account. If there is some sort of boundary layer getting formed on the asperities, we need to account. So we need to account all those aspects also. So this, in this case situation particularly, I say in this case particularly, friction was shown kind of in a stripe curve, which we have covered in the lecture 1, while in this case also normalized wear has been plotted, and you can see the behavior. This is the wear behavior, the friction behavior, the wear and friction, they are following almost similar kind of trend, almost it's not exactly. And here only in this situation in hydrodynamic lubrication you find the wear has dropped down to zero, almost zero, while friction is increasing. And that's why we say that we don't want to increase in the friction, because energy consumption is also important, it's not a wear only. So quite possible under mixed lubrication they are following the similar trend, where friction are following the similar trend, while coming to the hydrodynamic regime, or where the two surfaces are completely separated, then they are not following the same trend, they are following a different trend where it becomes a zero, friction is only important. But if you look at this region, in this situation particularly the surface roughness is playing major role. Now in this situation, if there is any film thickness, if zero film thickness, again the surface roughness will not play a role. But if there is any thickness, and we know that even the environment is quite friendly, metal surface cannot be remain virgin, there will be oxide film on that, and that will form the some sort of minimum film thickness on that. So that's very important for us to consider. While in this present course, we are highlighting, we are trying to describe something about the dryer case, but we will not detail much about dryer case. We really are not interested to know only the financial losses. We are more interested how to recover or how to minimize the financial losses. For that purpose, we will be covering mixed lubrication, we will be covering elastohydrolytic lubrication, and to some extent hydrodynamic lubrication. Again, I say in this case, this is a classical hydrodynamic lubrication, may not be required in the present time. So we'll try to give more emphasis on EHL and the mixed lubrication. However, mixed lubrication also requires some sort of HL, so I will be describing, but we will not give maximum weightage, or will not give a higher weightage to this side. Now, in this case particularly, if you look at a Sommerfeld number and this modified Sommerfeld number, what is the difference? Here they have used R by C square. So generally that is used for the bearing case. So that means this whole figure has been utilized, this complete figure has been given for the bearing case. However, it can be used for the any type of surface also, except this R by C. We can think about H minimum or specific film thickness. We can incorporate a specific film thickness in this case to get a better results overall, or maybe say give a better representation. Now we already have studied something like we really require a surface roughness. Now when we measure the surface roughness, we have two options. We have a 3D surface profilometer where the whole surface is really measured, and then we have a 2D stylus profilometer, and we will get a 2D curve, something like that. So these are the asperities you are able to see. This is asperity, this is asperity, this is asperity. Similarly, in this situation, these are the asperities also. So these are the important for us, and of course valleys are also important. In the present course, we will also say that we give maximum weightage to valleys, and peaks we know that in running in time peaks will be eliminated, will be trunk off completely. So what are the features? We say standard surface roughness parameters are average value, mostly manufacturer they give average value. Then we have a RMS value or RQ value, skewness value, kurtosis value, and peak value, RZ value in this situation. And for simplicity, we have shown this figure as a RZ is coming down or reduced in this situation. Like in this case, instead of 4.1, if it becomes a 0.46, you can see the coefficient of friction, initial coefficient of friction, as well as here coefficient of friction is decreasing significantly. That means this surface roughness, reduction in surface roughness is really helping to reduce a coefficient of friction. So that's why we really require. When we see surface roughness parameter and we are representing with R value, this is basically for 2D surface profilometer, when we stylize profilometer. When we go for the surface, or we say 3D surface profilometer, then instead of R we will replace with that. That's a nomenclature, as stand for the 3D profilometer and R for the 2D stylus profilometer. Now, what are the situation possible when the two surfaces come in a contact and make interface? That's what we are trying to show in this case. The two surfaces when they come in a contact, first possibility is the addition, and other possibility is a kind of a plowing or fracture, and while in this case it is causing a cracks and removing the from a surface. So this is important in the one aspect, and there's another aspect. So what we see, whenever the two surfaces, there's a contact 1 and the contact 2, whenever the contact regions are examined, we say it will really create a high stress. So that's what we have been shown in previous one on the previous slide, that the stress level will be higher. So almost a 5 to 6 time compared to nominal stress level what we have been thinking, and that's what we say is a higher stress than if the surface were smooth. When we account the surface roughness stress level will be on much higher side, and that high stress can distort, crack and fracture the materials. That has been point of interest to us, and that's why we need to really consider, and that will cause a wear or a higher wear rate. We need to account those kind of results, obviously wear out, and we need to really see what are the remedial action, because for sustainability minimization of wear rate is very important. So this is a very simple figure. We are showing that we have a Stellus kind of profilometer, and as it says, the surface roughness can be measured using the profilometer, in which vertical displacement is measured by sliding stylus, or we say it can be a diamond tip probe, because a diamond is very hard, and it will not cause the breakage so easily. That's why we use, and it can really work for the years. And we know that if there is a larger deviation of this stylus, and the recording will happen, and there is a, and the signals will be keeping recorded. So this is basically a kind of a vibration or the variation which stylus is getting when we are traversing from one position to this side, this position. So that is where the signal is being recorded. Now there are some sort of standards to calculate RA value, calculate skewness value, calculate RQ value, kurtosis value, calculate Z value. And this is what we can say block 1, block 2 surfaces can be measured using this kind of Stellus profilometer, and we get results like this. You can see here the RA value is a higher side 0.6, and RQ will be on a higher compared to that. It is almost 1.25 times to 1.3 times. Skewness has been shown a positive 0.05, and while kurtosis has been shown 3.43. Now there are two points to be considered. Whenever the skewness is having some value either more than 0 or lesser than 0, that means that indicates this is a not normal distribution. That means surface is not behaving a normal distribution curve. So this is very important, and many time the people assume, or researchers assume, or students assume there is a Gaussian surface. If there is a Gaussian surface, then skewness cannot be having a value other than 0. If skewness is other than 0, then it is a non-Gaussian surface. We cannot say it's a Gaussian surface. So this is important, and earlier also people used to think that kurtosis value more than 3 is a bad, that means surface has got a damage, while in this case particularly for tribology say, we said no, higher value of kurtosis are important to keep a good surface or keep a minimum tribology. So if kurtosis is a 10, I will not worry that much, but earlier people used to think about kurtosis should be lesser than 3, otherwise it will be harmful for the tribological purposes. So this is what we see RA and RQ value, and then we find other parameters also. Now here in this figure particularly we have shown RT as a maximal amplitude, and I ideally believe that RT is something like a highest peak and valley difference, or difference between the two values. This is lowest the point and the highest point RT. This indicates basically the what is the maximum variation possible. While coming to the RP is the highest peak value of any surface, while RV is a lowest one. Now people generally give more weightage to the RP, reason being that there are peaks and then these peaks need to be removed. So that's what the peak value should be given. However, the peak value RP is only 1, and RZ is something like a 10 peaks we take an average, we and get the results of that. So these are the important. We define here RT something as a total height roughness. It's a basically vertical distance, it's not axial distance, the vertical distance between highest peaks and lowest valley. And then here the important aspect has come something, it is used as we using evaluation length. What is the meaning of evaluation length? We'll be describing in the next slide. And we say this provide information, particularly the highest difference, which has a significance. That means we can say that whatever the manufacturing we are using, it may not be very good if RT value is on higher side. If it is keeping a lesser, that means manufacturing has been done proper way. So that is where there's some indication related to the manufacturing is being coming on the same. RP, as I already mentioned, is a maximum peak value, highest peak. Again, we are talking about evaluation length. That will be described in next slide, that what is the difference between the evaluation length and the sampling length. Reason being, these are statistical tools or statistical measures. Whenever we talk about the statistical values, naturally we need to talk about a sampling length. What is a sampling length? And instead of one sample, we need to take a more number of samples. So particularly when we go for the surface roughness, we take a 5 samples and average the value. So if I'm assuming, suppose if I'm assuming whatever they have written here, 0 to 200 is a evaluation length, this is a evaluation length, then I had to choose a sampling length which may be much lesser than this. And if I had to choose a 5, that means evaluation length in this case will be 1/5 of that. So that means I will consider this as a one portion, as another portion, then third portion, then fourth portion, then fifth portion, and then I will average out those values. So naturally we really require a good standards to follow, so that we get a reproducible results or repeatable results. Otherwise we will not be able to get. That's why we really require a good method to be followed. In this situation particularly, we will follow the ISO standards so that results are meaningful. Of course, all the equipment which are already there in the lab, they have inbuilt algorithms. They give a perfect value after doing all averaging, removing side effects also. Those things happen there. Now this is a stylus has been shown, particularly there is a stylus is really moving up and down in the valleys, and it really sending a signals to the computer. And we know that the computer, good thing is about the digitization. What is the meaning of digitization? Here we get a data, and when we get a data, we can process data as per our requirement. We can really say what is really more meaningful to us, and then we capture and then again repeat also. So if sometime we calculate RA value using the summation of all digitized point, that means this is Z1, this is Z2, Z3, Z4, Z5, Z6 something, and we take absolute value. We don't go with the negative, positive, absolute value, and divide by number of points, that's the RA value. However, assumption here in this situation is a mean is equal to 0. If mean value is not 0 in this situation, then we need to first find out the mean value of the signal. If it is 0, then there is no issue, but better to check it. Now here we have shown with the digitized one, here I am showing analog one. So both the things I am showing, whichever method is applicable, we can go ahead. Particularly computer one, we know this is for mathematical purpose. When we are utilizing for our computational algorithms, then this can be utilized. Otherwise for computer purpose, this can be utilized. Now if we calculate the mean value in the situation, and the mean value is a finite value, it is some say like and the 0.201, 0.02, it's not 0, then we, instead of this relation, we will use this relation z amplitude minus mean values, and then we will try to integrate or complete the sampling length. So here I'm using the word sampling, not evaluation length. So this is the sampling length, the sampling length, sampling length, sampling length, sampling length, sampling length, something. So this is what we are saying, that this is the sampling length, is not evaluation length. And then here where the RT has been calculated based on the evaluation length, RP is on the evaluation length. These are the important aspects to consider. And here that we are saying that we generally follow the standard. This is ISO 87 standard. RT has been defined in previous slide, RP has been defined in previous slide, RA value also how to calculate has been defined previous slide. We say the arithmetic mean surface roughness, average deviation of roughness profile from a mean line. That means if mean line is not at the zero level, then we need to find out the mean line, and then what is the deviation from a mean line, that is what we calculate RA value. And as I already mentioned, it is for the sampling length. We need to really think about sampling length, and sampling length in as per the standard, the 5 times of sampling length becomes evaluation length in this case. Now RQ is something, a root mean square value, which we are using for our tribological purpose. If you remember, we use a specific film thickness, something like H minimum divide by RQ1, or maybe RMS, we say RQ of surface 1 and RQ of surface 2, means B in this situation. So that's where we really required RQ for the defining what will be our lubrication domain. That's important for us. Again, in this case, all the 5 parameters, they can be defined in specified in micrometer or nanometer. These are important to quantify. Now other than this parameter, we require two more parameters. That's what we call skewness and kurtosis. Now reason being, of course, these are the dimensionless. Earlier 5 parameter what we mentioned, these are those were the dimension. Here we do a kind of divide by the standard deviation. In this situation, you can see here the sigma cube, sigma 4. Reason being, here is the cubic length, or the power cube and power 4, and this is what we have using here. That this is the sampling length, this is the evaluation length that has been shown. And here in whenever we use a profilometer, they use a traversing length also, and they neglect initial sample, and they neglect the final sample also. So this is as per the standards they follow. And then evaluation length, this peak values, value and RT is generally based on the evaluation length, not a sampling length. So these are the important aspects to be considered, particularly when we are trying to model, otherwise results will not be favorable to us. Now coming to the skewness and kurtosis, here we say that if there is a Gaussian distribution which has been in a public or in a tribology for the years, the people have been considering there is a Gaussian distribution, and more or less all analysis have been done on a Gaussian distribution. For Gaussian distribution, this skewness factor has to be 0. That means whatever above, what the equal to the below has to be there. However, for the tribological purpose in these days, we prefer to go with a negative value of skewness, and then we reject the positive value of skewness. This is a bad for tribological purpose, this is a preferable for the tribological purpose. And generally, at least I have come across with a number of surfaces, I don't find skewness as a 0, and there's no point to make it skewness also 0, because this has a preference over the others. I don't have to go for the surface texturing, because the negative skewness itself provides some sort of texturing to us, and that's important for us. And of course, more detail have been given in my book. I have picked up from this slide figures, particularly from my book itself. Now another one comes the kurtosis. As I said that initially thinking was the kurtosis lesser than 3 will be preferred, and this is for the kurtosis equal to the Gaussian distribution. And the initial thinking was that kurtosis more than 3 will be bad, reason being they were showing a very high peaks, and high peak is not really favorable from a tribological point of view. I agree with that, but we know these high peaks under running in can be really trimmed. So if there after trimming it will turn out to be like this, it will turn out like this, but valleys will not be having any effect. And if it is really trimming of highest peaks, and I'll get a negative skewness, and I'll get this kind of a curvature on this, so it will really help me from a tribological point of view. So that's why we say from tribological point of view, we require a negative skewness and high kurtosis value. It is very important to keep that in a mind. Now it is a important, already we have said that the roughness is a very important for us, and already have mentioned that the negative skewness describe area with a deep valley and there is a lack of high peaks. I'm using the word there's a lack of high peaks, there's a deep valley. That means depth side and the surface has a higher valleys or maybe say more inside. Well, in this case, this figure has been shown over here. You can see there's no peak in this case and there are valleys. So it's very difficult to manufacture. We need to really do some sort of polishing. So always a polishing action will help the tribology or will reduce the friction, will reduce the wear rate also. So that's very important. So that's why we say negative skewness describe area with deep valleys and like our high peaks. Why? High kurtosis value indicative of the high peaks and deep valleys. So we really require deep valleys. That is happening also negative skewness, and then even if there are some high initial peaks, that will be trimmed off. They will be will be removed from a surface during a running in period. So that's very important for us. That's why we say by combining both the parameter we can get plateau like smooth surface. That's what we are trying to show here. It will not be exactly like this, but it will be in this form. I'm just showing this is the ideal surface which we really require for tribological purpose. Ideal tribological surface, right? And then it really gives like a texture. In these days there is a lot of work going on the texturing of the surface. Here we choose it, go through running in, we will get a whatever we require a surface. So that's very important. So now to summarize in this, we can say that when two surfaces rub together, peak region usually gets worn away, core region bears a load. That means a peak, whatever the, like in this case if the peak has a worn out easily. Now core region is something, a core region here, it bears a load, that's a bearing the load. And the last one is that valley region, if I provide a lubricant, they will keep lubricant, they will retain lubricant, and that is very important for us to maintain that lubricant. It is very helpful for us to maintain this kind of lubricant. So overall we say that combo negative skewness and high kurtosis value, this combination will help us. So it is not only RA, it's not a RQ, it's not a RP, it's not a RT, but two parameters which are trying to emphasize, that's a skewness and kurtosis. That will change the scenario of tribology. That's more useful for us, for our purpose. However, major challenges are there which say once the surface start rubbing against another surface, asperity, height and shape distribution will change. It's likely to go under dramatic changes. That means we need to have some sort of model, or we say that computer model, or maybe say computational algorithm, which can really simulate all this behavior. What is the initial surface roughness or maybe surface profile? After few cycle, what will be surface profile? That's like we can want to simulate the running in behavior and then design completely from that angle. So this will be a major challenge when we, particularly for tribologists who are really working in this area, to really think well in advance what kind of surface will come out from rubbing in and when we are providing this kind of parameters. So this is very important to consider, and this is what I am just trying to show the reality that if you go through the book which was published by the Bartz in 1988, Lubrication of Gear, he has very clearly shown that before engaging gears in the work operation, and after that you can see here the milling itself, the gear when gear were milled, initial surface roughness varied from 2.3 to 4.6. Of course, in number of years it reduces to 1.2 to 2.3. That means I really don't really require a super finish operation uh, before engaging gear. Even the gears they can turn on they are the low speed and maybe a high viscous oil or and some additives, I can get a better surface after that. However, if I keep improving, that will give better and better results. Even after lapping or honing, like in this case, the roughness has been reduced to zero point 0.3 to zero point 0.6, still we are getting benefits in this situation. Of course, benefits are slightly lesser compared to what we are getting in a milled surface, but we know that if these peaks remain on hard side, it will cause a failure of the gears. So we'll prefer to go for the this kind of operation, grinding, lapping, honing, whatever. Of course, we know that the cost will increase in this case, particularly the cost increases with the super finish operation. However, another thing is that manufacturing plays a very important role in a tribology, that the surfaces which we are designing, are they manufacturable? If they are not manufacturable, then there will be problem for us. So what are the challenges in this situation? We can say the numerical model to examine interaction between the two bodies possessing rough surfaces, and almost every surface is a rough surface, and we need to really see how do we go ahead. Now, models to assess the impact of roughness on friction and wear. So first is a modeling, and then what will be the impact on the friction and wear. So really require sophisticated models for this purpose. Then we say the models necessitate inclusion of the typographical representation. So if I have a typographical or maybe say 2D surface available, 3D surface available, am I able to reproduce in our algorithm? If it is, how am I really quantifying? Am I getting all the parameters the same which were measured? If it is, then only I can go for the next iteration. Otherwise, I will not be able to go for the next iteration. So taking that surface and then reproducing the same surface and with the same parameters which have been measured, exactly same, with some mathematics, with some logic. And finally, we say generate realistic surface topography that will occur under dynamic operational condition. So this is a very important. So we are trying to forecast under dynamic situation what will happen. That will be a important, we say major challenge to do this kind of modeling and get a good results for us. This is there any other challenge? Yes, there are other challenges also. We say we are measuring using the stylus. Now stylus has a finite dimension. If whatever the roughness value we are getting, that value will be decided by only stylus. If a stylus is not thinner or maybe say smaller in a size, then I may lose some valleys and peaks also. Chances of losing peaks are slightly lesser, but surely valleys we are able to see here we have lost this value. So that's a very important aspect. There is a limitation, so we need to go for this more sophisticated equipment for that purpose. One more challenge which I realize is that following ISO standards. Reason being, whatever the values or a value we get, they come to the some standard, they follow some sort of class. So ISO class N1 means surface roughness will be something like a 0.02, 0.025 to 0.05, and 2 is something 0.05 to 0.1, and 3 is something 0.1 to 0.2. So these are the surface roughnesses in this situation. Now for each surface roughness, we have to have a different sampling length. That's what we mentioned. If the surface roughness is something like 0.025, the sampling length should be something on order of, we value something like a 0.08 mm. Now, if surface roughness has gone from 0.05 to 0.04, then surface this evaluation the sampling length can be 0.25. Then we say the 0.8 to 1.6 micron surface roughness. Here the sampling length has to be 0.8 mm. And last in this situation, 3.2 to 12.5 micron sampling length need to be 2.5. So this is iterative. Unless we understand this, we incorporate in a model, we will not be able to find out the right value, we will not be able to match the values properly. So understanding this is very, very important. I am just trying to show quickly in 1 or 2 minutes that what we have done. This is a surface roughness profile of one of the sample, you can see here the sampling length has been maintained something like a 2.5 mm, and then we are getting RA value 0.1. So RA value 0.1 should have a sampling length something like a 0.25. It should not be 2.5. So this is an important aspect. That means we have unnecessarily taken more bigger length and we need to reduce this sampling length. Now we reduce that one. Instead of that, we say the sampling length should be 0.8. Again we get a 0.08 here. So if I go back and check, is it the 0.8? Also it should require the zero point 0.8 here, something like that. So in this situation, on the 0.08 something which comes in here, so that means there is required sampling length of 0.25. 0.8 sampling length is not sufficient for 0.08. That's why we taken now finally 0.25 to find the roughness, and we are finding the roughness again has changed. That means when I'm changing the sampling length, surface roughness has been changing. So it depends on what is the sampling length. It is not I'm calculating RA value 0.5 and I become happy with that. Now what is the sampling length? Whether that has been calculated, measured appropriately or not. If it has not been measured appropriately, then there will be issues, there will be problems in the situation. So that's why we say now the reducing cutoff length has effect on attenuating. Main thing is a greater portion of larger wavelengths, because we say surface roughness is restricted to smaller wavelength, not a longer wavelength, and that need to be accounted when we do modeling in this situation. So that's how important for us. Reason being, this is a surface roughness profile, as the profile of the surface. Now roughness is having very low wavelength. Waviness is slightly on the higher side, form is on slightly higher side. That means we need to have some sort of filter which allows a smaller wavelength to pass, not a bigger wavelength. That means whenever you do a mathematical model, the bigger wavelengths of the related to waviness should be stopped. Otherwise, it will really create some sort of noise. Again, wavelength related to form should be stopped. Otherwise, it will create a more it's a noise. It will not be true roughness. So this is what we really require to quantify tripod interface. It's important aspects for us, and we need to understand these things. And we say with this I'm trying to close this lecture. Thank you for your attention.